Welcome folks, J Lamb Bio here, and yes, it is the day that you all have been waiting for. I know you've been super excited about it, all 5 of you that have contacted me requesting this. I just can't contain my excitement anymore. We are diving into AP Chemistry. Now, I know that some people might say, well, Mr. Lamb, you're doing this because you teach it. No, I am doing this for the people and my students, but also the people. We're talking today about mole concept and mass spectrometry. So with every video, I always like to start off with student learning objectives. I think it's important that you know exactly what you are supposed to get from the video, and I'll try to keep it short and give you guys 2 or 3 things to focus on. So today you're going to be able to calculate a variety of factors using moles, molar mass, atomic mass units, and Avogadro's number, and explain mass spectrometry and evaluate that spectrometry data. So I'm not going to go through all of the different molar conversions. These are things that should be review for you guys, but keep in mind that 1 mole is 6.022 times 10 to the 23rd atoms, molecules, or particles. Again, that is a conversion factor between moles and atoms, molecules, or particles. It's also called Avogadro's number. The molar mass is how many grams per mole there is in something, and that's typically found on the periodic table. So if the molar mass of carbon is 12.01, the molar mass of nitrogen 14.01, the molar mass of oxygen 16, etc. Atomic mass units refer to the mass of an individual proton or neutron, and then we actually use that to kind of build an atom, so to speak. So, for example, an atom of oxygen 16 would have 16 atomic mass units. Oxygen 17 would have 17 atomic mass units. Remember that 16 or 17 that comes after it is the mass number. So just kind of keep those things in mind. And then atomic mass units and molar mass tend to be equivalent to one another. Carbon 12, you'd have 12 grams per mole, but it's 12 atomic mass units per atom. So there's a variety of different conversion factors that are here, but do keep in mind that you can convert between moles and molecules. You can convert between moles and grams. If you want to go between grams and atoms, you have to go through moles. And then atomic mass units and molar mass tend to be equivalences of one another in terms of the number, but do have different units. Now, mole fraction is a way to measure the concentration of a solution, or just really the concentration of anything. And with mole fraction, we have moles of solute divided by moles of solution. So the example given here is that there's a solution that's prepared by adding 16 grams of C3OH, okay, or methanol, to 90 grams of water. The mole fraction of this solution is closest to which of the following? Well, we need to go ahead and calculate that, okay? So in order to do that, we need to convert both to moles, because we need moles of solute and moles of solution. Remember that solution is solute plus solvent. So my first component is methanol. So I have 16 grams of methanol. Okay. We're going to convert that to moles. So for every 1 mole, there's 32 grams. Okay. I'll take 16 divided by 32, that is 0.5 moles. Simple enough, okay? We'll do the same thing for the bottom one, because we're dissolving that into water. So we start off with 90 grams of water. Molar mass is 18. 1 mole. And what we're going to get here, we put it into the calculators, we get 5 moles. Now, to determine the mole fraction, again, we take our moles of solute, and we're going to divide that by our moles of solution. Remember that our solution is our solute plus our solvent. So we take 0.5 divided by 5.5. What we get is roughly 0.09. Now, there is no unit for mole fraction, so you can just leave it in its number value. All right? Let's move on. So just a couple other review calculations that we might have here. The first one is density. Excuse me. Wow. Rough morning. Density is mass divided by volume. Remember that mass can be in grams. That mass can be in kilograms. Volume is either milliliters or centimeters. Milliliters is if it is a liquid. Centimeters cubed typically if it is a solid. Percent error is actual minus theoretical over your theoretical multiplied by 100. Remember that is always a positive value, because percent error is the absolute value away from the theoretical value. Your percent mass, take the molar mass of an atom divided by the molar mass of a compound times 100. Atoms in a compound, We convert to moles, and then we kind of look at the subscripts, and that really helps us figure out how many atoms we have. Okay. So, for example, here we have a student that has a 10-gram sample of calcium bromide. How many atoms of calcium and bromide are there in the sample? Well, we have a problem that starts with grams, and it's asking us for atoms. So the first step is always going to be convert that to moles. So let's start doing that. So we have 10 grams of CaBr2. We're going to convert our grams to moles. And again, we find that information on the periodic table. Molar mass of calcium bromide is 199.87. Okay. So again, let's get that into moles first. Let's do a little bit of math. And what we get is 0.050 moles of CaBr2. Okay? So that's our first step. But the question is asking how many atoms of each particular component we have. Well, if we have that many moles of calcium bromide, you need to look at the subscripts. So that's going to be the same number of moles as calcium because there's only one calcium atom per molecule of calcium bromide. Okay? So in 0.50 moles of CaBr2, we are going to have 0.050 moles of Ca. Okay? For bromine, it's a little bit different because there are 2 atoms for every 1 molecule. So in that instance, we actually have to double the amount of moles that we have. So that's 0.10 moles of bromine. Okay? So just kind of keep that in mind that the subscripts really help us determine how many atoms there are in that particular compound. So your next step then would be to use Avogadro's number and convert that to atoms and to convert calcium to atoms. Okay? One thing that you'll notice, and again, if you're doubling the amount of moles, essentially the number of atoms of bromine would be double that of the moles of calcium as well. So just kind of keep that in mind as you're looking at those calculations in your homework. Let's move on. Another review calculation I want you to take a look at is the average atomic mass. Now, the average atomic masses are essentially the molar masses that you find on the periodic table. It is a weighted average of all of the naturally occurring isotopes of that element. So what you do is you take the sum of the masses of every isotope multiplied by the abundance. So if you look here, we have 3 naturally occurring isotopes of neon. Neon 20 has a mass of 20, neon 21 has a mass of 21, and so on. The percent abundance, though, most of the mass is in neon 20. 90.48% of neon atoms are neon 20. 0.27% is 21, and 9.25% is 22. So we multiply each individual mass by the percent abundance, and then what we do is we take all 3 of those numbers and add it together. Thus, the average atomic mass is 20.2. Now, if you look at the numbers, this actually just makes sense if you think about it, because most of the mass of neon is in neon 20. So it makes sense that the average atomic mass, since it's a weighted average, is closer to 20 than it would be to 21 or 22, because 21 or 22 has less percent abundance than neon 20. So just kind of keep these things in mind as you may be asked to do some calculations related to this. The last concept I want to cover, which is a really cool concept, is mass spectrometry. And this is an instrument that measures the mass to charge ratio of atoms. So you know that in a particular sample of an element, you're going to have a variety of different isotopes. This actually helps us separate the isotopes based on its mass to charge ratio. How do we get the charge on it? Well, atoms in the ion source down in the bottom left are bombarded with electrons to create ions. Now typically all of these atoms will have the same charge, so all of those isotopes will have the same charge. Those ions then are passed through a tube with a strong magnetic field. This actually helps separate the individual isotopes, because heavier isotopes are not going to be as impacted by the field as smaller isotopes, which separates them when they hit a detector. So there's actually a little bit of a curvature to that magnet. That curvature actually allows those individual isotopes to separate. And then there's a detector on the opposite side that detects the number of hits that it takes. And then that actually outputs a ratio that is put into a graph. Here's a couple of examples of mass spectrometers. The one on the top right is a replica that was used by J.J. Thomson. He was the discoverer of the electron. The one on the left-hand side is one that was kind of used during World War II, and if you actually look at the bottom one on the right, that's actually used by one of the Mars rovers to investigate the different constituent components of the elements that are found on Mars. Very fascinating. So one thing we can actually do with this information is we can look at the data, and this is a typical graph that you would see in a mass spectrometry problem. The y-axis is the relative abundance. You typically don't get an amount with this, but it's relative to one another. So as you can see here, most abundant isotope is with a mass of 70, the x-axis being the atomic mass. Be careful. Remember that it is the atomic mass, not the atomic number. There's a difference there. Remember, the atomic number just refers to the number of protons. Atomic mass is protons plus neutrons. We know based on this information that the average atomic mass would be closer to 70 than 74 because the relative abundance of the mass of 70, the relative abundance of the isotope with the mass of 70 is greater than that of 72 and 74. And then also based on this information, you could actually calculate the average atomic mass. As you look, you have the relative abundance there. So 9 out of the 16 components that are here, so you see I got 9, 6, and 1. So there are 16 So 9 out of the 16 numbers there would represent 70. So you could take 9/16 and use that as a percent abundance and then use that for your calculation. Same with 6. You could say that's 6 out of 16, use that for relative abundance, and 1 out of 16 for relative abundance as well. So again, lots of different ways that you can calculate data using this, and we'll investigate this later on. So hopefully you guys have a really good understanding of the student learning objectives. I really look forward to working with you guys this year. Again, we've got a lot of great new content coming out. Make sure you like and subscribe to JLam Bio. Make sure you leave a comment down below. Just kidding, you can't. But best of luck to you guys. Have a great day, and we will talk to you later. Bye-bye.